Gas and steam turbines represent the cornerstone of modern power generation technology, converting thermal energy into mechanical work that drives electrical generators. These sophisticated machines have evolved significantly since their inception in the late 19th century, now achieving remarkable efficiency levels and powering the majority of the world's electricity generation infrastructure. Steam turbine history. The steam turbine revolutionized power generation with its invention by Sir Charles Parsons in 1884. Parsons built the first practical steam turbine specifically designed to generate electricity, with early machines producing only a few kilowatts of power. By the early 1900s, technological advancements had enabled steam turbines to reach multi-megawatt scale, making them increasingly viable for industrial applications. The fundamental advantage of steam turbines over their predecessors, reciprocating steam engines, was their ability to operate at much higher speeds with greater efficiency and fewer moving parts. This led to steam turbines becoming the backbone of electrical generation in thermal stations, including coal-fired, nuclear, and gas-fired steam plants. The technology continued to evolve throughout the 20th century, with improvements in materials, blade design, and thermal efficiency. Gas turbine history. The concept of the gas turbine dates back to 1791 when John Barber patented the first design, though practical implementation would not come for more than a century. The 1930s marked a significant milestone when Brown Boveri built the first practical gas turbine for power generation, demonstrating the viability of the technology. The development accelerated dramatically during World War II with the invention of the first jet engine-based gas turbine for aviation by Frank Whittle in 1941. This breakthrough paved the way for post-war developments in heavy-duty industrial gas turbines designed specifically for power generation and mechanical drive applications. Today's modern F and H-class gas turbines represent the pinnacle of this evolution, with single-shaft units capable of exceeding 400 megawatts of power output and achieving remarkable efficiency levels, particularly in combined cycle configurations. Gas turbines, working principles and types. Working principle. The Brayton cycle. Gas turbines operate on the thermodynamic Brayton cycle, which consists of four main processes. 1. Compression. Ambient air is drawn into the compressor section, where it is pressurized through either axial or centrifugal compression stages. Modern axial compressors typically feature 10 to 20 stages and can achieve pressure ratios of 15 to 1 to 30 to 1. 2. Combustion. The compressed air enters the combustion chamber where fuel is burned at constant pressure. Modern combustors use advanced designs such as annular, canannular, or silo configurations, often incorporating dry low NOx, DLN, burners to minimize emissions. 3. Expansion. The hot, high-pressure combustion gases expand through the turbine section, where they drive the turbine blades, producing mechanical work. This section typically includes both high-pressure turbine, HPT, and low-pressure turbine, LPT, stages, with blades featuring sophisticated cooling technologies including internal cooling channels, film cooling, and thermal barrier coatings. For a power distribution, approximately one-third of the power generated by the turbine section is used to drive the compressor, while the remaining output is available for the generator or mechanical load. Major types of gas turbines. By application, aeroderivative gas turbines are adaptations of aircraft engines, featuring high efficiency, lightweight construction, and rapid startup capabilities. They are commonly used in LNG facilities, mechanical drive applications, and peaking power plants. Notable examples include the GE LM2500 and LM6000, Pratt & Whitney FT8, and Rolls-Royce Trent 60. Heavy-duty industrial gas turbines are designed for rugged, long-life operation with greater tolerance to fuel impurities. They are primarily used for baseload power generation and combined cycle applications. Leading models include GE Frame 6, Frame 9, and 9HA series, Siemens SGT5-8000H, and Mitsubishi M501G/M501J series. By fuel type, gas turbines can be classified by their fuel compatibility. Natural gas. the most common fuel source due to its availability and clean combustion characteristics. Liquid fuels, including diesel, Jet A, and kerosene. Dual fuel systems, capable of automatic switching between gas and liquid fuels. Hydrogen-burning turbines, an emerging technology for zero-carbon power generation. Syngas/biofuel capable, designed to operate on alternative fuel sources. Cycle variants, simple cycle gas turbines achieve 35 to 40% efficiency in heavy-duty applications and offer fast startup times, making them ideal for peaking power plants. Combined cycle, CCGT, systems utilize the exhaust heat, typically around 550 degrees Celsius, to generate steam for a steam turbine, achieving total efficiency levels of 60 to 64% with H-class turbines. CHP/cogeneration systems provide both electricity and useful heat to industrial users, achieving very high total thermal efficiency of 85 to 90%. Intercooled gas turbines remove heat between compressor stages to improve mass flow and efficiency, while recuperated gas turbines recover exhaust heat to preheat compressor air. Steam turbines, working principles and types. Working principle. The Rankine cycle. Steam turbines operate on the thermodynamic Rankine cycle, which involves the following processes. 1. Steam generation. A boiler or heat recovery steam generator, HRSG, produces high-pressure, high-temperature steam by heating water. 2. Expansion. The steam expands through the turbine blades, converting thermal energy into mechanical work. As the steam expands, its pressure and temperature decrease while its velocity increases. 3. Condensation. The exhaust steam is condensed back into water in a condenser, creating a vacuum that enhances the pressure drop across the turbine and improves efficiency. 4. Feedwater return. The condensed water, feedwater, is pumped back to the boiler at high pressure, completing the cycle. Types of steam turbines. Based on steam flow direction, impulse turbines utilize steam expansion in nozzles before it strikes the blades, converting pressure energy to kinetic energy in the nozzles rather than the blades. Common designs include Curtis stages, velocity compounding, and Rato stages, pressure compounding. Reaction turbines allow steam to expand as it passes through both stationary and moving blades, with both pressure and velocity dropping across the blade rows. Parsons design is the classic example of a reaction turbine. Modern turbines typically employ a mixed impulse reaction design, combining the advantages of both types for optimal performance. Based on exhaust pressure, condensing turbines exhaust steam to a condenser operating at very low pressure, maximizing the energy extracted from the steam and achieving high efficiency. These are commonly used in power plants. Back pressure, non-condensing. Turbines exhaust steam at higher pressures suitable for industrial processes, providing both power and process steam. Based on stages, single-stage turbines have a single set of nozzles and blades, suitable for small-scale applications. Multi-stage turbines feature multiple pressure stages, typically organized into high pressure, HP, intermediate pressure, IP, and low pressure, LP, cylinders, allowing for more efficient energy extraction. Based on steam source, steam turbines can be powered by various steam sources. Coal boilers, traditional fossil fuel steam generation. Gas turbine HRSGs, in combined cycle power plants. Nuclear steam supply systems, in nuclear power plants. Biomass boilers, using renewable fuel sources. CSP, concentrated solar power using solar thermal energy with molten salt storage. Steam turbine components. Turbine casings are designed to contain the steam at various pressure and temperature conditions. HP casing, designed for high temperature, high pressure steam. IP casing, handles intermediate pressure steam. LP casing, contains the low pressure steam and features large last stage blades. Rotors and blades come in different configurations. Rotors can be disc type, with separate discs mounted on a shaft, or drum type, solid cylinder with machined blades. Blades consist of a root, fir tree or dovetail attachment, airfoil, aerodynamic profile, and either a shroud or freestanding design. Valves control steam flow. Main stop valve, MSV, provides emergency shutdown capability. Control valves, CV, regulate steam flow for load control. Reheat stop valves, RSV, isolate reheat steam during emergencies. Intercept valves, for control reheat steam flow to IP section. Auxiliary systems support turbine operation. Lube oil system, provides lubrication and cooling for bearings. Gland sealing system, uses steam to prevent air leakage. Condenser and vacuum system, creates low pressure for steam condensation. Feed water system, returns condensate to the boiler. Future of gas turbines. Hydrogen-capable burners represent a significant trend toward decarbonization, with manufacturers developing burners capable of operating on up to 100% hydrogen in the future. This transition leverages existing gas infrastructure while enabling zero-carbon power generation. Closed-loop supercritical CO2 cycles offer potential efficiency improvements by using supercritical carbon dioxide as the working fluid instead of air, allowing for more compact equipment and higher thermal efficiency. Advanced blade cooling technologies, including transpiration cooling, will enable higher turbine inlet temperatures and improved efficiency. These systems use porous blade materials that allow cooling air to pass through the blade surface, creating a protective cooling film. Ceramic matrix composites, CMCs, are replacing traditional nickel superalloys in hot section components, offering higher temperature capability, lower weight, and reduced cooling requirements, which collectively improve efficiency. Digital twins and predictive maintenance leverage artificial intelligence and machine learning to create virtual replicas of physical turbines, enabling real-time performance optimization and predictive maintenance scheduling. Future of steam turbines, advanced ultra-supercritical AUSC, steam cycles push steam temperatures above 700 degrees Celsius, significantly improving thermal efficiency compared to traditional supercritical systems. This requires advanced materials capable of withstanding extreme temperature and pressure conditions. Large nuclear turbines are being developed for Generation 3+ reactors and small modular reactors, SMRs, featuring specialized designs to accommodate the unique characteristics of nuclear steam supply systems, including very large low-pressure sections with extremely long last-stage blades. Carbon capture integrated steam cycles are being designed to work seamlessly with carbon capture and storage, CCS, systems, with optimized steam extraction capabilities for the energy-intensive carbon capture process. Gas and steam turbines have evolved significantly since their inception in the late 19th century, now representing the cornerstone of modern power generation. Gas turbines offer rapid startup capabilities and high power density, making them ideal for peaking applications and combined cycle configurations. Steam turbines provide exceptional efficiency in baseload applications, particularly when integrated with gas turbines in combined cycle plants. The future of turbine technology is focused on improving efficiency, reducing emissions, and enhancing operational flexibility. Hydrogen-capable gas turbines and advanced ultra-supercritical steam cycles represent pathways to decarbonization, while digital technologies enable more intelligent operation and maintenance. As the energy landscape continues to evolve, gas and steam turbines will remain critical components of the global power generation infrastructure, adapting to new fuels, operating conditions, and grid requirements while continuing to provide reliable, efficient electricity for decades to come.